Hello everybody, welcome to my class. Today I am going to discuss about relation between velocity, radius of circular path and the angular velocity, or you can say angular speed. So here, although this is part of circular motion in mechanics, it has some further application in other chapter as well, for example in Hooke's law, and also in the dynamics of rigid body and in other chapters as well. So here let's see V. Here V stands for linear velocity, and you know that V, if that is velocity, then you can say rate of change of displacement, that is the change in displacement point in time, and if this is a speed, if you call, then that is the rate of change of distance, and R is the radius of the circular path. And omega is, in fact, it is called angular velocity or also angular speed, you can say. And here this is defined as in the way it defines that rate of change of displacement is velocity. So here rate of change of angle is the angular velocity. Okay. So if you talk about the unit of the velocity, you know that displacement in meter and then time in second. So SI unit is meter per second, but here SI unit is in fact theta is in radian. In the circular measure, theta is measured in radian. So this is radian and this is second. So its unit is radian per second, or you can say rad per second. Now let's try to establish the relation between these three identities. So here you know that in any circle, if you are given any circle, for example, and from the circular measure, you know that this is center, this is R, and this length is S, and it is Christ angle theta over here. Then relation between R and RS and theta is theta equals to S by R. Alright? Or you can also say S equals to R theta. So here theta is in radian. That is, in the circular measure is in fact the radian measure. Now, in order to prove this, what you can see, we'll check this letter. So firstly, let's consider a circular motion. Alright? So here it should be a complete circle. So for example, a particle is at position A and moving in this direction. So that means it is tangent to here, and say its speed is V, and this is the center. You can call it as O, and center and joining the circumference line is called, it is the radius of this circle. And next you can see here, in some time the particle is at this position, right? And you can call this position as B, okay? And the velocity is this. So what you say here, that the object is circulating with constant speed. So here two things are here. As the motion is circular, we cannot say that its motion is velocity over here, because the direction is being changed at each and every point. But at some particular point, what you can call, for example, at some particular point here, this angle is described angle del theta, for example, at some particular point, it has some particular direction. So this sort of velocity can be represented in terms of vector for this point. Okay, and for this point also this is the vector. But in fact, throughout the motion, although the speed is constant, we cannot say that the velocity is constant. In fact, we are taking the speed constant, but at some particular point, it is the velocity in particular direction. So only the change is due to the change of direction, not because of change of its motion. Alright. So we'll discuss about the same in my next class. So for now, let's see here. In very small time t, what happens? The particle is from point A to B, describing angle del theta at the center. Now, if you compare with this circle, this should be arc length S. But as this is very small amount of change we are taking here, so instead of writing S, we write here del S, this arc length. So in fact, these two are not with the equal opening here. It's a very A and B are very close to each other as B tends to A. So we are taking a very small gap. So here this is the in this case you can call here in time delta t, the change in angle is del theta while the object is going from position A to position B, describing the arc length, very small scanty arc length as delta S. So now start from here, we have in general S equals to R theta. Now differentiate both sides to t. So we have here now del S by del theta equals to, as for a particular circle we take R as constant, otherwise there will be, although the direction may not be changed, but there will be some difference in while finding the difference delta S. So we take R constant for a particular circular motion. That's why we don't find the derivative of that. So another part we have derivative of del theta y with respect to dt. Now what we can say in this case, like here you apply the limit del t tends to 0, and here also you can apply limit del t tends to 0. What happens when delta t tends to 0? So t means there is some time, and if it is going towards 0, that means what happens? This del theta will also go towards the 0 value, that is, this will also tend to 0, and in fact this will also tend to 0. In this case, what do you see? It will be difficult to say that whether this is a straight line or the curved line. Okay, so at this point, while changing the angle by del theta, what you can say, the object change the distance from A to B by the amount delta S. So delta S can be taken now as the change of distance. So here, by definition of calculus, what you can write, like this means it is ds by dt equals to, this is R, then d theta by dt is del theta by dt is d theta by dt. And you know that ds by dt and d theta by dt. ds by dt is in fact the change in distance or displacement by time that defines the velocity or speed, and R, and this defines omega. So this way we establish the relation between Vr and omega in a particular circular motion. Okay guys, if you have any question, please drop your question in the comment box. So thank you for watching.